Good morning, everyone. My name is Kiat and I'm from Hitachi Vantara. I'm the tech expert for data management and protection in the APAC region. Today, I'm honored and privileged to be able to share with you a topic from Hitachi. In this particular presentation, we will cover something called Polyphased Erasure Coding for scalable storage systems. This is really a erasure coding technique that has been invented by Hitachi, and it tries to address certain shortfalls in the traditional erasure coding that is already in the market. In today's agenda, we will start off with an introduction on what's the trend in the market, as well as some of the hardware technology that is available today. Secondly, we will cover what are the existing technologies. Thirdly, we'll cover what are the challenges of these existing technologies. Of course, then we will have coverage on our solution, which is the polyphased erasure coding and how it serves to address some of these challenges in the market. And we'll follow on with a conclusion. So let's move to the introduction and some background. Today, there are two major trends that we see in the market. Firstly, there is a distributed storage systems that are coming into the market with products such as software-defined storage. Some products that come to mind are Scale.io from Dell EMC. At the same time, we also have open system software, where we try to have SDS as well. Some examples are Ceph, Gluster File Systems, HDFS, and so on. The other major trend that we are seeing today is the implementation of hyperconverged infrastructure that is becoming quite popular. Now, these two trends try to take away or move away from custom-built, purpose-built hardware storage arrays. Instead, they try to use general-purpose servers and try to simulate and implement a scale-out storage with just a software layer on top of commodity servers. So keeping this in mind, there are also some other technologies that will come into play. First of all, our drive performance with the implementation of NVMe drive media is allowing drives to perform at a much higher rate. For example, one NVMe drive today can give you about 2,500 megabytes per second or 2.5 gigabytes per second. Now, if you put 10 of these drives in, say, a DL360 from HPE, we will be able to aggregate about 25 gigabytes per second. Compare that with Ethernet switches nowadays, where we can have 10 gigabytes, which up to 100 gigabits per second Ethernet switches. That means in terms of gigabytes, we can transfer about 10 gigabytes for network performance. As you can see here, 10 of the NVMe drives can outperform the bandwidth of the Ethernet switches. In the software-defined and hyperconverged infra environment, Ethernet switches will potentially become a bottleneck in our software storage world. So that is something that is to be taken into consideration when we implement our software-defined storage. One other thing for our introduction that I would like to talk about, and that is erasure coding and replication. What do I mean by that? For on the left side, you can see replication, which means that we want to protect our data by using multiple copies. So for example, if you have a 1 terabyte logical volume, we want to be able to protect it with 3 physical copies at the back. That means that the capacity we require will be 3 times as much for a logical capacity of 1 terabyte. The 3 terabytes of physical capacity is required. For erasure coding, we break the logical data into 4 pieces and we spread them out to different storage nodes. We couple that with protection by using parity calculation to be able to reconstruct the data if we ever lose 1 or 2 of these storage nodes. That means we have 2 parity calculations. In this example here, we have data with 4 pieces followed by 2 pieces of parity. The capacity overhead in this case is 1.5 times of what we need to serve to the application. So if you have 1 terabyte of logical capacity, we will need 1.5 terabytes of physical capacity. Now let's move on to the existing technologies in the market. We will talk about data writing first. That means updates to our storage. In this case, we have again the 2 examples, replication as well as erasure coding. On the left with replication, you can see that we have applications that are writing data. And the first row of colorful blocks that you see there is really the data that's received from the application into the storage node. The storage node is represented by a box, and it is really a commodity server with a storage software layer running on it. Now, the second row of colorful blocks that you see is where we store the data into the drive media within the storage node. In this example, where P is equal to 2, we have 2 redundancies. For every piece of data that is written by the application, we need to replicate it to 2 other storage nodes so that we can recover and tolerate 2 storage node failures. Here, you can tell that for every piece of data that comes in, we need to send 2 copies of the data across to the other storage nodes using the Ethernet switches. So for this example here, where we have 4 blocks of data, we need to send 8 copies or 8 blocks, 4 blocks to storage node 2 and 4 blocks to storage node 3. Now compare that with erasure coding, where we have D equals 4 and 2 parities. Here we break the data up into 4 different sections, and each section is sent to a different storage node. On top of that, we do calculate 2 parities, and the parities are also sent across the network to the other storage nodes as well. In this case here, we will have 5 transmissions across the Ethernet switches, right? 1, 2, 3, 4, and 5. And this is obviously more efficient than the replication technique, where we have to send 8 transmissions. Remember what we said just now, where network cost or overhead may become a bottleneck. So we'll try to keep the network traffic as low as we can. So erasure coding for writes will be more efficient in terms of network bandwidth. Now let's move on to data read. What happens when we read the data? As you can see here in the replication technique, when the application asks for the data, we don't need any network traffic in order to retrieve the data. We just read locally from the storage media, and return the data back to the application. So in this case, replication technique is more efficient for reads. In contrast, look at erasure coding. When we have an application request, the storage layer needs to retrieve data from the various nodes. So for this case, we have 3 transmissions over the network in order to piece the 4 blocks of data together before we return it to the application. So in terms of efficiency of the network, in a read situation, erasure coding is actually worse off. So in summary, we have a table below here where we have replication and erasure coding columns. And on the left, you can see the various parameters that we are looking at to improve on in terms of efficiency. So first of all, we have the capacity efficiency, whereby you can see replication is not so good. We need 3 times the physical capacity versus erasure coding, where we only need 1.5 times. In terms of performance, it's a mixed bag. Read-wise, for reads, replication has 0 network transmissions. But for writes, replication has got higher overhead, has got higher overhead versus erasure coding. And lastly, for reliability, in our examples previously, both have the same amount of redundancy. That means we can tolerate 2 storage nodes failure at the same time for both solutions. So there are pros and cons for replication versus erasure coding. So there's no perfect solution today that we can use. So Hitachi actually set out to solve 2 challenges. The first challenge for erasure coding is to eliminate the network traffic for read processing, so while maintaining the capacity efficiency. So really, what we want to do is have capacity efficiency, at the same time have 0 network overhead. The second challenge we want to address is for us to do a write processing and maintain the same efficient network overhead as well. It's similar to the erasure coding schemes of today that is in the market. So in this case, we want to have more efficient network transmissions for writes also. In effect, our goal is to achieve the best of both worlds. So let's move on to how we address challenge number 1. So for challenge number 1, as a reminder, we want to actually eliminate the read processing while maintaining a capacity efficiency that allows us to reduce how much physical capacity we have or we need to store the data. So approach number 1 is to make sure that erasure coding localizes the data component of our placement. Let's give you an illustration for this. Let's assume we are having a write from the application. In the diagram below, you can see the reference on the right, where we have the replication technique, as I've explained earlier. And we also have the erasure coding technique that was also discussed previously. Now, on the left side is our solution that we want to use to address challenge number 1. We have erasure coding of 4 plus 1 parity in this example. You have your applications writing your data to the various storage nodes. Now, again, I would like to emphasize that the first row is really the data that is received but not yet hardened. In effect, it's just in the memory of the storage node. The second row is where we have the data that is hardened onto the storage media or the drive media. Here, you can see in this example where the first storage node received the updates for all the RAID blocks. Now, we want to store all the RAID blocks locally so that we can reduce the storage network traffic. And then we take the data, one piece of data, and transmit it to storage node 2. Storage node 2 will aggregate all the data from the first block of every other storage node. With all the aggregation, then we can do a striping of the parity calculation across the different nodes for the first block. And that parity is represented by a triangular block here, as you can see. So in this way, we want to reduce the network transmission. For the second block, the same thing will happen. The second block from each of the storage node, for example, will be consolidated into storage node 3. So the blue second block, the green second block, and the purple second block will also be consolidated and transmitted here. Now, once we have the blocks transmitted, then we will calculate the parity of the second blocks across all the storage nodes and store it in this triangle here. So this is repeated for all the other blocks as well. With this approach, then we can allow a very efficient read method, because every time we read the data, we don't need to traverse across the network, but instead we just get the data from the local storage. So that is how we address challenge number 1. And we have basically maintained a very efficient and low network traffic for read processing while maintaining the capacity efficiency of an erasure coding solution. Now on to challenge number 2. For write processing, we also want to maintain the same efficient network overhead as the erasure coding scheme that you see in the market today. And that is the next slide will tell you how we want to approach challenge number 2. Now, the initial approach in this example, as you can see, is when we have the original data represented by the pink storage blocks below. Now, the new updates will come in and it's represented by the red storage blocks. Now, whenever there's an update like that, we will, in terms of RAID operations, we will read the pink blocks and do an XOR operation with the red blocks. That will give us an intermediate result, and that intermediate result can be used to calculate the parity. Now, once that is done, we can then harden the data from the red blocks in the memory into the storage media in the last row. With this intermediate XOR result, we will transmit, or we will need to transmit the data twice. Each block of data has to be transmitted once to the next storage node and another one to the other storage node, because we have 2 parities that we need to calculate. So this is the initial approach. As you can see, with this approach, we will need to transmit 8 blocks of data. And these 8 blocks, if you compare that with the traditional replication technique here, the 8 blocks is not very efficient. We want to actually achieve a 5-block transmission instead. So we have optimized this approach in the next slide. But before I move on to that, I would like to say that the XOR result, if we do another XOR with the original parity, then we will be able to get the new parity, which we can store into the storage media. So that's the reason why we need to transmit the XOR intermediate results to the different storage nodes. Okay, now let's go on to see how we can optimize this. In this next approach, which is optimized, what we do is this. We will do, when the data comes in from the application, as you can see on the red blocks here, we will calculate a parity. And this parity is then sent across to the next storage node for consolidation. Now, storage node 2 will consolidate the data blocks from the other storage nodes, and we can do a parity calculation. And this parity calculation will enable us to do a parity storage of the first protection. But at the same time, with this consolidation of data, we can do another calculation for the Q parity. In the red terminology, the first parity is called P, and the second one is called Q. So the second parity can also be calculated from the same consolidated block of data. So in this way, we eliminate the second transmission of the block in order for us to calculate the second parity. So that is how we solve this challenge. Now you may ask, are there any disadvantages to this approach? Well, we don't live in a perfect world, so there is a bit of disadvantage. For example, we cannot do a full stripe write. Now, in the custom-built purpose-built storage hardware array, we tend to have to drive efficiency in the backend by consolidating all the updates and then doing a full stripe write into the drive media. But for our case here, because we are splitting the blocks up, we are not able to consolidate and do a full stripe write. So how does that work? Well, we think that network transfer efficiency is more important than the efficiencies of a full stripe write. And we've mentioned that network will potentially become the bottleneck in a software storage defined world. So this technology is based on the premise that local drive performance will outshine or outperform the network performance. So we believe that the benefits of this approach will outweigh the disadvantage of having a full stripe write. Now, going on to my last slide, which is the conclusion. What we want to say is we've managed to combine the best of both worlds, the advantages of replication technique when we have zero reads in terms of network traffic, and we also achieve the efficiencies of erasure coding in terms of capacity. So we have only 1.5 times the capacity. At the same time, we reduce the network traffic for writes as well, using the technique that we have derived. So with the polyphased erasure coding from Hitachi, we now can achieve the advantages of both techniques and be able to have that redundancy of tolerating storage node failure up to 2. So that is the conclusion. And with that, I would like to leave you with a supplement, which is a white paper that's available in IEEE website. The link is shown below. Here you can find more details of the solution that I presented previously. And with that, I would like to thank you for your time, and we'll take some questions from now.